Hi friends, good morning. Welcome back to another session from Design of Steel Structures subject. So today I am going to start new topic, that is design of tension members. So earlierly in the previous subjects like strength of materials, you have gone through different types of members. What are these members? Tension member, compression member, like that you have seen. And even in our introduction to steel structure subject also, we have discussed the different members, that is elements of a steel structure. Means steel structure is a rigid frame structure formed by connecting different members. Those different members are nothing but tension member, compression member, like that, right? So here we are talking about today regarding the tension member. Okay, tension member means what? A member which is purely carrying tensile load, tensile force, is nothing but called as a what? Tension member, which is also known as a tie member. Okay, now where you can see these tension members means, if you see the trusses, right? Okay, if you go for any indoor stadiums, function halls, you will be seeing different types of trusses, right? Now in that, this is nothing but a tie member or a tension member. Tie member, or which is also called as what? Tension member. Okay, next, bracings in a building. Okay, horizontal members. Okay, and if I take the suspension bridge, the rope is like this. Okay, these suspenders are also nothing but called as what? Tension members. Next, cables in a cable stayed bridges. Cables in a cable stayed bridges. Some bridges will be there. Next, cable stayed bridges will be there. Next, if you go for any cement factory or any other big factories, to transfer the material, to transport the material, they will be using rope like structures from one point to another point. Okay, so in that the rope will be there, right? In those situations we will be calling as a tension members. Now what are the different forms we can use as a tension member? Okay, the different forms of tension members are, means these are the members in a structure. Now what different shapes can be used? That is different forms of tension member. Different forms of tension members means a solid rod can be used as a tension member. Okay, next, a flat plate can be used as a tension member. Okay, next, angle section, that may be a single angle section, okay, or double angle section, all these. Okay, next, a tube like structure means hollow. Okay, this is tube, single angle, this is what? Double angle. Okay, next, T section. Okay, next, channel sections placed back to back or toe to toe, it depends upon the condition. Okay, next, multiple angle sections. Multiple angle sections we'll be using as what? Tension members. Okay, even I section can also be used. Okay, these are the different forms of tension members in a different steel structures. Okay, in a different steel structures is nothing but called as a tension member. Okay. Next, we'll see the difference between gross area and net area. Gross area and net area. Okay. Now gross area means, suppose if I am going to connect this member to any gusset plate. Okay. If the member is connected to a gusset plate. Member is connected to a gusset plate. Say for example, if it is connected by, connections are there, right? Welded is there, riveted is there. Okay. Next what? Bolted is there. These are the three different types of connections we have learnt across the earlier classes. Now, if it is connected by welded or riveted or bolted, whatever it may be, if I am considering total area without deducting the holes that are made for riveted or bolted. Generally, for a member to be connected by welded, there is no need of deducting any area, right? Suppose if I want to connect two members by using riveted or bolt, I have to make some holes, right? So the total area of the cross section available without deducting these areas is nothing but a gross area, and area of cross section after deducting the area of holes is nothing but a net area. Okay, means net area equals to gross area minus area of holes. You have to deduct the area of holes from the total gross area available, so that you will be getting the net area. Okay, this is the difference between the gross area and the net area. Okay, now one of the terminology which is very important, that is called as a shear lag. What is this? Shear lag. Now what is this shear lag? Suppose for example, a member is there. Okay, I am loading here this edge. Okay, and apply a load, just like a pull. Okay, now because of this load, stresses will be developed inside the member. Okay, but the stresses and strain developed at this edge where we loaded will be differing from the stresses developed in the other place of the member. Okay, means there will be a variation of stress or strain in the member for the same loading. For the same loading, the stresses developed in the member will be differing. Okay, now how it will be differing means, the edge where load is made will be having higher stresses and strains than the edge where no load is made. Okay, that is nothing but shear lag. Lag means what? Some variation in the shear. Okay, so that is nothing but called as what? Shear lag. Means the normal stress distribution and deformation in a flat near the end where forces are applied are non-uniform. Means what? More normal stresses are elongation at the loaded edge and less normal stresses are elongation at the unloaded edge. This phenomena, which is due to variation of stress deformation, is nothing but called as what? Shear lag. Okay, you remember this one, very important one. Okay, so I will write the definition here. The normal stress distribution the normal stress distribution and deformation. In the flat, this is a flat one, right? In the flat, near the ends where forces are applied, okay, is non-uniform. What it means, okay, higher or more normal stress and elongation, or next one is what, less normal stress and elongation. Now in which place means loaded edge will be having this one. If I loaded like this, will be having more normal stress and elongation, and this is unloaded edge. We are not applying it the loaded the other edge. This phenomena of variation in the stresses within the same flat for the same application of load is nothing but called as what? Shear lag. Okay. Next, we'll see the failures of tension members. Okay. Now, types of failures of a tension member. Okay, failure due to yielding of gross cross section, cross section, or rupture of net critical section, Next, block shear failure, Okay, these are the three types of failures we can expect in a tension member. And while designing the tension member, we will be checking with respect to yielding, rupture and block shear. Okay. Next one is maximum slenderness ratio. Okay. What is this maximum slenderness ratio? What is this slenderness ratio means? It is denoted by lambda, which is equals to, it is a ratio of effective length by the corresponding radius of gyration, or gyration, whatever it may be, right? So lambda equals to KL, this is effective length, by gamma. Okay. Now, there as per IS 800, okay, 2007, it is recommending the maximum slenderness ratio values of three different types. First one is what? 180. Okay. Next 350. Next 400. These are the what? Maximum slenderness ratio as per table number 3 of IS 800 2007. Now, what are these three different values? Why they are showing differently? Okay. Suppose if a member is there, okay, tension member, okay. Now a member will be failing, any member. Suppose I take an example as a tension member, okay. Tension member will be failing if at all, if it exceeds its limit. That is one condition. Other than that, if any other reversal of stresses in the tension member may occur, in that situation it will fail, okay. A member which may fail due to exceeding of its limit or any reversal of stresses that may occur. Reversal of stresses means we have designed it as a tension member, but suddenly some reversal of stresses happened, and means compressive load is coming onto that one, okay. In those situations, the tension member will fail. Now, if a tension member in which the reversal of direct stresses occurs, reversal of direct stresses occurs due to loads other than wind and earthquake loads, okay. Wind and earthquake loads tension member in which reversal of stresses is happened, but not because of wind and earthquake load. In that situation, the maximum slenderness ratio value will be having of 180. Next, a member, okay, in a tie in a roof truss, tie member in a roof truss, okay. In this, in which reversal of stresses occurs due to wind or earthquake loads. If at all the reversal of stresses in a tension member occurs because of wind or earthquake loads, then the maximum slenderness ratio value is 350. Now the tie member in a roof truss is designed in such a manner that it will be taking compressive loads during this wind or earthquake loads, okay. Next, 400 is the maximum slenderness ratio for a member always under tension, member which is always under tension is nothing but what? Slenderness ratio maximum of 400, which is always under tension, means no reversal of stresses will be occurring, This topic is very, very important while designing, and especially for ESET point of view. Not only ESET, any competitive exam, this one is very much important, okay. Next, as I said you earlier, the design strength of tension member, a tension member whose maximum loading capacity can be obtained from these three values, okay. It is A, B, C. A and B and C, right? Now, how you will be deciding is design strength due to what? Yielding of gross cross section. Yielding of gross section. Okay, this is denoted by tension, right? DG, gross section G. So TDG. Next, due to rupture strength of critical section. This is net rupture of critical section. It is denoted by TDN, net section. Okay. Next one is block shear. It is called as what? Block shear. It is denoted by TDB. Block shear. Now here, based upon these three values, the lowest of these three will be considered as what? Sorry, that ink has been spreaded completely here. Okay, the least of the three values, that is lesser of TDG, TDN and TDB will be considered as its tensile strength. It's a tensile strength. Okay. Next, we'll see the how these to be obtained, this TDG value, TDN value. Okay, from code book around page number, wait a minute, second, I'm seeing. Yeah, if you can see here, page number, it is around 31. Next to 32 page, you will be having section 6. Under that you will be having what? Design of tension members. Okay, in that, see, this is what design strength means. First one, design strength due to yielding of gross section, cross section, that is TDG. Okay, now this is what? Design strength due to yielding of what? Gross section. For that, so see, this is the formula. Okay, that is TDG equals to AGFY by gamma m naught. This is the formula. Okay, this is as per page number 32 of IS 800 2007. Okay, now what is this AG? Okay, AG is nothing but what? Gross section, cross section. Okay, now in the earlier introduction class, we have studied regarding the partial safety factors, right? So under loading condition, the partial safety factor will be how much? It is has to be 1.10. And what is Fy? Yield stress of material. Yield stress of material. This is regarding the what? Yielding of gross cross section. Okay, next, Second one is what? Design strength. What strength this is? Due to rupture of critical section. What is this? Rupture of critical section. Okay, see, next one is what? Design strength due to rupture of critical section. For plates it is there. Okay, next for threaded, for single angles it is there. Okay, now this is the formula for single angles. If you can see, that is how it is denoted. It is denoted by TDN, which is equals to 0.9 ANCFU by gamma M1 plus beta AGO FY by gamma M0, where beta equals to, very big formula is there, that is 1.4 minus 0.076 into W by T into Fy by Fu into Bs by Lc, which should be less than or equals to Fu gamma M0 by Fi gamma M1 greater than or equals to 0.7. Means minimum, beta minimum is how much? 0.7. Okay, and beta max is how much? This formula. Okay, means the value you are obtaining with this formula should be in between these one, in these two. Okay, should be between these two. Now what is this ANC and what AGO means? Suppose a gusset plate is there. To this gusset plate you are connecting the angles. Now ANC is nothing but area, net area of connected leg. This is the connected leg. Next, gross area of outstanding leg. Net area of connected leg, this one. This is what? Gross area of outstanding leg. Okay. Next, gamma M0 is nothing but what? Partial safety factor for material under yielding, and M1 is nothing but partial safety factor for material under rupture. How you will be taking? For rupture it is 1.25, that is gamma M1, and for yielding it is 1.1 gamma M0. All these are studied in your previous classes, right? Next, what is Fu? Ultimate stress of the material. Fy, yield stress of the material. In the earlier classes you have studied yield stress and ultimate stress when you are seeing the mechanical properties. Okay, in that you have ultimate stress, that is Fu, and yield stress as Fy. Okay, next one more terminology is there, T, the thickness of the leg, T. And what is W? This is W. Okay, now what is BS? That is nothing but width of shear lag in case of welded connection. In case of welded connection, you will be taking W equals to BS. But in case of what? See here, it is clearly mentioned. Angles with single leg connections. Here, if it is welded like this, BS equals to W. And if it is connected like this, what will be the BS? BS equals to W. Okay, W plus WL minus thickness. Okay, so while doing the problems we'll try to check these values. Meanwhile, this is the formula for what? Design strength yielding due to rupture of critical section. And next, third one is what? Design strength due to block shear. Design strength due to block shear. Now in this block shear, it is denoted by what? TDB. TDB. Now here TDB1, which equals to AVG Fy by root 3 gamma m0 plus. So AVG Fy by root 3 gamma m0 plus 0.9 ATN Fu by gamma m1. Okay, and TDB2 is equals to 0.9 AVN Fu by root 3 gamma m1 plus ATG Fy by gamma m0. Okay, now this is as per what? These are the two formulas. In that, what is this AVG, ATG, AVN? Means here V stands for shear, V stands for shear, and T stands for tension. Okay. Now AVG or AVN, it is nothing but area under shear. Next ATG, ATN, this is area under what? Tension. Area under shear and area under tension. Right? Now suppose if I am connecting a angle section, this is a gusset plate, I am connecting what? Like this, welded here and both completely. Suppose this is the gusset plate. Okay, to that gusset plate I am connecting an angle section. Okay, and what I done is I am doing welding all round. These are side bends. Just imagine, and these are end weld. Now which plane will be under shear? Means if I apply a tensile load, this portion, this plane will be what? Under tension failure plane. We call this as what? Tension failure plane. This plane is called as what? Tension. Because I am pulling, it will be subjected to a drag. It will be subjected to a drag, means it is a tension failure. And this pulling will be normal to this one, but this is parallel to these planes. This load pulling is perpendicular to this one, but parallel to this one. Means parallel means what? This is shear failure plane. What is this called as? Shear failure plane. Okay. Now how you are supposed to take these areas? these areas. Means, suppose area under tension means whatever the length of the connected leg multiplied with the thickness of the plate. Okay, connected leg plus multiplied with the thickness of plate will give the area under tension. Okay, next, area under shear. Area under shear, that is length of weld into 2 into thickness of plate. Both sides, right? Length of weld into 2 into thickness of plate is nothing but the area under shear. Okay, so these are the 3 formulas which are very important. And coming to what we say, a tension member designed which is connected with a welded joint will be more effective in taking the loads. Okay, a member means a tension member which is made with welded joints will be taking more load, means more effective than that of other bolted and riveted, because in a welded joint we are not deducting any thing for bolted or riveted. Okay, because gross area equals to net area. Okay, whereas in riveted and bolted, because of connecting those, what we are doing, we are making holes for connecting the tension member with respect to riveted or bolting. We are doing, we are deducting the holes, we are making the holes. So the gross area will not be equals to net area will be less than the gross area. So area available will be less compared to welded joints. So that is the reason the design tensile strength of tension member connected, okay, with fillet weld will be greater than the member connected by riveted or bolted. Is it okay? So this is the introduction part of design of tension members. Okay, based upon these 3 formulas available, we'll try to solve problems. Okay, we'll try to solve problems, main problems in the next class. Meanwhile, we'll see one small 3 marks question from this topic, only 3 marks. Okay, that is, calculate the design strength of a tie, means tension member, ISA 100 by 75 by 8 mm due to design strength due to yielding of gross section. Take Fy equals to 250 Newton per mm square. This is the question given. Okay, now given data. Okay, given data. Here, what is that? ISA 100 by 75 by 8 mm. 100 by 75 by 8 mm. Now, for this, the area of Indian standard angle section you may be getting from steel table. But As steel table is not available, even though we can calculate it. AG equals to 100 minus 8 by 2 into 8 plus 75 minus 8 by 2 into 8. Okay, so how much you are getting? 100 minus 8 by 2 means 100 minus 4, 96 into 8. So it is 768 plus 75 minus 8 by 2 means 75 minus 4. Okay, so it is 71 into 8. Sorry, 71 into 8, 568. Okay, which is equals to plus 768. How much you are getting? 1336 mm square. This is the gross area. Okay, and the yielding. Now what is the formula? TDG equals to AG Fi by gamma m0. What is AG? 1336, and Fi is given as 250 divided by gamma m0 is what for yielding? 1.10. You should remember these values are, even the code is there, into 250 divided by, okay, so it is 303636 newtons or 303.636 kilonewtons. This is the basic formula, this is problem, which is 3 marks for 3 marks. Okay, further in the next class we'll try to solve more number of problems on design of analysis and design of tension members. Thank you for watching my video. Please do subscribe and share with your friends. Okay, thank you.